All right, so this is how the LIGO Observatory works. Actually, sorry. It's an acronym, so I need to capitalize it all. Okay? The LIGO Observatory works like this, where they have light and they have a mirror. And they send this light ray through a mirror that's partially silvered, so light can go through it. And then it comes out but bounces off of one mirror that way and one mirror this way. And these lengths here are miles long. So it's several miles long, so the light can bounce there, bounce back there. And then when the light comes together, they combine it together and analyze it. Why do you do this? Well, what happens when a gravity wave hits the Earth is it actually takes material and it compresses it and stretches it. But it does this to about a trillionth of a meter. It's so tiny that you never even notice it. In fact, Einstein was the one that predicted that these gravitational waves existed, but he said, I don't think it will ever be possible to detect them. Well, in the 1930s when he was discussing this, it was impossible. But nowadays with lasers, they send this laser which has an exact precise wavelength. And they bounce it off one side, bounce it off the other side, and these are tuned to exactly the wavelength, distance-wise, of the light, which is about the trillionth of a meter. And if the gravitational wave comes through, then this distance will shift by about a trillionth of a meter, and this one will stay the same. If the gravity wave comes from that way, that one will shift, and this one won't shift. So they're going to compare this distance and distance. Well, you can't compare it by measuring it. It's impossible to measure that shift. But if you combine the light, one's a wave, one's a trough, if they combine together, they cancel out. Or if they combine together with two tops, two crests, it doubles it. You can measure that. And that allowed them to measure these gravitational waves. And this was really exciting. They'd been working on this since the 90s, but it wasn't discovered until about 4 years ago that they actually found the first thing. What did they find? Well, the first thing they found was black holes merging. But then they later found two neutron stars merging together. Those neutron stars merging together caused the short gamma ray bursts. All right, so this is another thing. What I really want you to know is what a gamma ray burst is, why we first detect them. We first detected them by looking for gamma rays coming from nuclear testing on Earth, and that there's two types. There's long and short. The long gamma ray bursts come from the type 2 supernova or the core collapse supernova. It occurs just as the core collapses into a black hole. It sends a jet of gamma rays shooting out the end of it. Short gamma ray bursts come from merging neutron stars. All right. Now, why is that bad for Earth? Not bad right now because all the gamma ray bursts are so far away. But if one of these occurred close to us, if a core collapse or the other kind, doesn't matter, and it shot gamma rays right at the Earth, so we were right in the beam and it was only 40, 50 light years away, we would be in big trouble. Remember how bad gamma rays are? They pretty much kill everything. So that would just plow right through our atmosphere. Usually our atmosphere protects us, but you can't protect us if there was this massive amount of gamma rays coming through. The gamma rays would come through, we'd all get radiation poisoning, and we would all die thereafter. Not immediately, it would take a while, but it would be a painful death. So, good thing is just like supernova, they have to come from supernovas, emerging neutron. There's none of them close enough to us, and the odds of it actually happening and pointing directly at the Earth are slim. But it's interesting to think about, and you need to read this chapter in the book. All right, that's it for gamma ray bursts.